Hi, thank you. Well, thanks everyone for coming here in the morning. I'm Catalin from INRIA Paris, and I will tell you more about our formal definition for compartmentalization. And that this is joint work with 9 fabulous co-authors, and with whom I've been working over the last 2 years on this. And as you heard, that's the key to success. Have 9 co-authors and everything is good at CCS this year. So we are talking about compartmentalization, and the main use of compartmentalization today is to defend against devastating low-level attacks like buffer overflows. And in a way, the root of this cause is insecure languages like C, where something like a buffer overflow can have catastrophic consequences on the security of the whole application. So this is a simple programmer error, but the consequences are very big. And it's not just buffer overflows. In a language like C, you have hundreds of different so-called undefined behaviors. And any of these if any of this happens, then, well, the program does something arbitrary, but the compiler and the standard doesn't guarantee anything for your whole program. And this includes things like use after freeze and double freeze, invalid casts, signed integer overflows. I mean, this is like a very common programming error that you sometimes forget to check upper bounds for integer variables, and if they're signed and if they overflow, the standard says it's undefined, and many of the compilers aggressively exploit that. You're not going to encounter that situation, which means if you do, you lose the guarantees for the whole program. So this is the root cause, but it's very challenging to fix, and there are many reasons for this. But really, the main one is efficiency. Like the reason the C standard lets these things undefined, the reasons the compilers exploit the absence of such undefined behaviors is because, well, this allows them to get away with checking for bounds on buffers, for overflows on integers, and these kind of things that would be expensive otherwise. So that's the reason this problem is still there after many decades of it being there. And this work and compartmentalization in general doesn't try to solve the problem, it tries to mitigate it. So the idea is that by breaking up your security critical applications into mutually distrustful components with clearly separated privileges, then you're somehow going to restrict the scope of this undefined behavior. And the idea is, well, it's not enough to do this at the source level. I mean, you have to preserve this abstraction of components going down. You need to separate components in memory to ensure that they have the right privileges, to ensure that they interact in the right way, say using calls and returns, that they pass values to each other of the right types. So there is the need for enforcing security when you go down. And the responsibility for enforcing security in this case, well, in a way is shared between the different parts of the compilation chain. So this, of course, includes the compiler, but it also includes the linker, the loader, the runtime system, the operating system, and even the hardware can give you features that allow you to enforce compartmentalization. So in a way, I'm calling all these things a compilation chain. So everything that starts from your source language, well, going all the way down. And of course, the idea is to build these secure compilation chains based on existing efficient enforcement mechanisms. So one easy way, or if you want very coarse-grained compartments, is to use operating system processes that are isolated between each other. And this is, for instance, what web browsers do with plugins or with tabs today. Other techniques include software fault isolation, where you get finer granularity, hardware enclaves, WebAssembly modules, capability machines, dark architectures. There are many ways you can enforce this. And somehow by enforcing this, we expect that you would get strong security. In particular, you expect that you would get some security guarantees that if you work hard enough, you could make watertight. Say beyond just, well, I'm increasing attacker models, so some attacker effort. Beyond just vague notions of security, that you could get something strong. And the intuition goes something like this. I mean, if a vulnerability appears in a component, this doesn't immediately destroy the security of the whole application, because components are protected from each other, and also because each component receives protection up to the point at which it itself could become compromised, for instance, by a buffer overflow. So this is common intuition for people working in this field of compartmentalization. And what we set out to do in this work is, well, can we make this intuition formal? Can we precisely define what is a compartmentalizing compilation chain supposed to enforce? So this is what we set out to do. And the main result of this paper is a formal definition expressing end-to-end security guarantees for compartmentalization. Now, the big challenge when you're trying to formalize security mitigations is that in order for your definition, for your security notions to be useful, you want them to give you source-level security reasoning principles. You want it to be easier to reason about the security of an application that is compartmentalized in the source language. So that's what I call source-level security reasoning. And this is you'll see how we achieve this, but you want to do this in this case even in the presence of undefined behavior, and undefined behavior cannot be expressed at all in the semantics of the source language. That's the reason it's undefined. If I show you a snippet of code and it's cropped at the bottom, but it just does return 0, so it's not very interesting. So if I show you 5 lines of code, which is the simplest vulnerable program that copies a buffer from its argument into a fixed size static array that's not without checking bounds, and I'm asking you, okay, what does this program do? I mean, just by looking at the source code of this program and by the semantics of the C language, all you're going to tell me if you find a bug is this program is undefined. What does it do? Well, maybe it starts a calculator. You're not going to be able to tell me that this starts a calculator by looking at the source of the program, right? So that's the problem. The source language doesn't tell you what happens after an undefined behavior happens. All you know is that the global guarantee, or globally, your program has no meaning and could do anything. Now, however, there is hope, because in a way, a compartmentalizing compilation chain can help you restrict the scope of undefined behavior. And in 2 ways. The first one is the more obvious one. In a way, you restrict the scope of undefined behavior to the component that actually causes it. That should be the component that becomes compromised, not the whole program. So this like spatial scope. So because we are protecting each mutually distrustful component from each other, the spatial scope of compromise is restricted. What's maybe a bit more interesting is we also want to restrict the temporal scope of undefined behavior. We want a model of dynamic compromise in which each component gets guarantees as long as it has not encountered undefined behavior. I mean, it's okay if a component has vulnerabilities, right? You might be talking about components that are hundreds of thousands or millions of lines of C or C++, in which case, yes, it's almost a theorem that it's going to have some vulnerabilities in it. So it's not just about, well, does the component have vulnerability, therefore it's compromised. It's more like, unless these vulnerabilities are actually exploited, and up to the point at which these vulnerabilities are actually exploited, you still expect to get guarantees for these components. So this is the model of dynamic compromise we want to support, and actually are the first to support in this definition. And this requires restricting the temporal scope of undefined behavior. So now, if you do this, you can formalize a security definition. And I'm going to show you, well, half informally, but it's quite close to our actual formal definition. And what this is saying is a compilation chain is secure if whenever you compile a compartmentalized program and you obtain a trace T, you link the components, you run it on the machine, and you obtain a trace T, then this trace T can be explained in some way in the source language. And before I explain you how this trace is explained, well, some notation. So I'm assuming this example compartmentalized application with 3 components, C0, C1, and C2, with interfaces I0, I1, and I2, which captures their privileges. And they're all compiled and then linked together and run to obtain a trace T. And this trace T, well, it captures the interaction of your whole application with the external world. So this will include things like system calls, input and output from the user, from the network, and this kind of thing. So stuff that's completely external to your application. So that's what we put in the trace T. And now we would like to explain this trace T in the source language. And the way we do this is by a sequence of component compromises. So if you get this trace T in the target, then there exists a sequence of component compromises in the source that explains this trace. And this is the first step of a potential first step in such a sequence, which says that if you execute C0, C1, and C2 linked together in the source, then you obtain a prefix of T called M1, followed by an undefined behavior. So this is saying that you can explain a prefix of T in the source language, after which, well, an undefined behavior happens in component C1, and afterwards you can no longer explain anything in the source language. If your compiler wasn't secure, you would globally lose guarantees at this point, right? This is already capturing the dynamic aspect of compromise, though, because up to the point at which C1 is compromised, well, it was all fine. But now, kind of, we would like to say, hey, now C1 is compromised, so what will happen with C1 afterwards? And what we do, and what our definition says, is that there is a way to replace the code of C1 with arbitrary code, A1, so attacker code, and then continue execution and obtain a longer trace or a longer prefix of the trace that's M1 and M2. So what this is saying is, well, the scope of undefined behavior is spatially restricted to the component C1. Now it can do arbitrary things. It could try to compromise other components. It could send them bad inputs, but it was still going to behave as a source level component. So it's going to interact with other components via calls and returns and this kind of things, not write arbitrary memory or this kind of low level stuff. So and it won't cause itself undefined behavior again, A1. So this is the kind of game we repeat. Now, well, maybe A1 sends a bad input to C2 and C2 falls over. Which is there on the slide. Like now we have an undefined behavior in C2. And well, if you have an undefined behavior in C2, then we also replace C2. Now we know that well, once we replace, we already replaced A1, now we also replace C2 with A2. We know that, well, we can produce an even larger prefix of the trace. And we do this until we can reproduce all the trace. And in this case, well, I'm assuming I can reproduce all the trace. In the worst case, you would have to replace all the components. And then, well, yes, you would reproduce the trace, but with everyone being compromised. And that can happen. I mean, in the end, if you didn't write your compartmentalize application well, then maybe one compromise can spread over and take over your whole system, right? And that's not a failure of the compartmentalization mechanism. That's a failure of the application, right? You wrote. One thing to note is that we've used this finite trace T in a couple of ways. Once we used it to record which component encounter undefined behavior, this undefc1 and defc2 at the end of the trace. And this is quite standard. For instance, CompCert would at least record that there is an undefined behavior at the end of a trace. But what it also allows us is to go back in time. I mean, you saw that when we replaced U1 and with A1, we didn't continue execution from there. But what we did is we went back in time to the beginning of the execution. We did the replacement, and then we re-executed along the same trace. So along the same, say, sequence of inputs and outputs from the outside world. And this is something that, well, this trace enables. To be able to rewind execution. And well, here we've rewind the execution twice until we could get to a situation which could explain the whole trace. So that's the main idea of how we can explain this trace T in the source language, by this sequence of executions where some components get compromised, execution gets rewound, and then I can explain more and more of the trace. So this explains both, well, how comes you got the final trace in the end, but also, well, how comes there was this sequence of compromises that led in the end to that trace. So this is the definition. We've also built a proof of concept secure compilation chain in Coq, and it has a few parts. So it starts from a compartmentalized language with buffers and procedures in which, well, components can interact via strictly enforced interfaces, recording, well, which other procedures from other components they're allowed to call. Then we compile this to a RISC abstract machine that also has kind of compartmentalization built in. So this is an abstract machine, more like an intermediate level, after which we have different backends at this moment too, in which you can choose, well, how exactly are you going to enforce compartmentalization. And the first way we do it is using a tag-based reference monitor, something we call micropolicies. We've been working on it for quite a long time. It's a special hardware in which each memory and each register has a large metadata tag, and this is propagated via reference monitor. We use a quite clever scheme to ensure things like the fact that you return to the right place. We use linear capabilities for that. And then, well, the other backend is complete software, no special hardware. It's a bare-bone machines without any protection whatsoever. And we rewrite the code of the components, and we add a shadow stack in a kind of vanilla software fault isolation style, and we obtain the same kind of guarantees. And for this first step stage, we verify things in Coq. It's a quite large proof, 23,000 lines of Coq, well, proofs and definitions, but mostly proofs. However, the nice thing about this proof now is that it's quite generic. So we hope to extend it, for instance, to the micropolicy machine as well. But for now, we haven't done that. What we have done is Coq has this quick check plugin that allows you to test properties. So we take the same property, like our definition, and instead of proving that this backend satisfies this property, we try on many input, many programs, and compartmentalize them and see whether there is anything violating our property, and we didn't find anything. So this is like a first step towards also having a proof there. And it's all on GitHub. To wrap up, So I explained about this formal definition characterizing the security guarantees of compartmentalizing compilation. This is the first definition to support this model of dynamic compromise. And the main idea there is that you have to restrict the scope of undefined behavior both spatially but also temporally. We have a proof of concept secure compilation chain in COC and two backends, one based using software fault isolation, the other using this hardware accelerated tag-based reference monitor. And not just our definition is generic, but also our proof technique. So we expect them to extend and scale quite well. So I'm not sure, probably I won't have time to tell you, but if you want, you can ask me in which way we plan to extend this. And I guess I have to take questions.
Thank you very much. Use the microphone for asking questions.
Hey, so this is interesting. I feel like I'm missing something, though. The security definition that, at least, so I should look at your paper, but the security definition as you gave it, I'm not sure quite what it buys me above just telling me what I get from C. So it seems like there's something that you're not telling us about interactions being only via the interfaces, which wasn't really showing up in your security definition.
Yeah. So that's not really part of your definition because in a way it's more part of your source language, right? So in order to apply this, you have to change your source language, say change C, to have components and have components interact in a certain way that satisfies certain static interfaces and privileges. And if you have that, then what this definition buys you is preservation of a certain class of safety properties. So what it doesn't buy you, which you might wonder, is what about hyper safety? What about things like confidentiality? And this is indeed one of the things on the to-do list. We have a recent draft in which we show, we explore how you can go beyond safety, including to hyper safety and confidentiality, but not yet in the context of also have an unsafe language. So we still have to combine these two pieces.
So if the components aren't defending themselves with these interfaces that you had drawn, then I don't really understand what you're getting from the security definition that you don't already get from the definition of that the C semantics gives you.
Well, the definition, the definition of the C semantics would tell you that as soon as you have an undefined behavior, your program globally loses guarantees, right? Well, now, what I'm telling you is your program has an undefined behavior. It's only that component that loses guarantees, and the way that it can affect the other components is only via, high-level interaction in C. In the safe subset of C, if you want, without undefined behaviors.
I see. So the interface by which they're interacting is the language semantics interface, and not some arbitrary low-level thing. Okay. Well,
so there's two things. There's that, and then we have a notion of static privileges, and in a way, if in your original C code, certain components wasn't importing a certain procedure from some other component, then the fact that it gets compromised doesn't give it access. So there is some notion of access control, if you want, in which components have interfaces and we feel like module interfaces, and just being compromised doesn't allow you to access more procedures, for instance, more system calls, than you could before getting compromised. So there is also that aspect, but the first part is also that, it's also sticking to the semantics of the safe part of the language.
Okay, thanks. One more quick question.
Over here. Carl Gutzer, University of Illinois. So it seems like what you need here is something like an illustrative case study to show us what this is good for in more detail. That'll be really challenging to do that. Maybe you could talk a little bit about what it would take.
Yeah, so at the moment, we have a very simple language, and so it's hard to to build a case study in detail. We have some example in the section 2 of the paper where we show, well, one example application with 3 components and what would it take to compromise it, and how this is, well, how you can reason at the source level using the kind of reasoning principles we provide. But I agree, this is like a toy example. I mean, once we can scale this up to say more of C, we should be able to, I don't know, build a little web browser or web server or something that has different components running in, say, tabs running in different components or this kind.
You kind of promised us you could handle Heartbleed.
Well, okay, or a web server, and then you can handle Heartbleed.
Thanks very much, Emily.